today we have a special guest, namely Julian Shun from MIT will give a guest lecture. So Julian did his PhD at Carnegie Mellon University a few years ago, and then he was for a short time at a postdoc position at the West Coast, I think. Yes, at UC.
Yeah, it was at Berkeley. Yeah.
And then he very quickly and very shortly after his PhD got an assistant professorship at MIT. So it's a picture book career so far, and I think with a very good reason for it. I think he has every year some of the nicest results on parallel algorithms. In particular, very often it's a interface between theory and practice. That's the kind of stuff I like most, and that I also think is the most of the most long-term importance. And today he will tell us something about, I think, on the one hand, the general principles he's using to design parallel algorithms, but also give us a glimpse on some recent concrete results. And I'm reasonably confident that you are able to understand much of this because we introduced many of the basic building blocks for parallel algorithms already in the lecture. Yes, so besides that, I maybe give Julian, give the word to Julian. He can slowly start with his lecture. It will be about an hour. Julian, would you allow questions in between, or would you prefer them to have them at the end? Or?
Yeah, people can ask me questions. Yeah, just feel free to interrupt me if you have any questions.
Okay, so
yeah, great. Well,
the blackboard is yours. So what do you say for a virtual lecture? So thank you.
Yeah, yeah, great. Thanks a lot, Peter, for the introduction and also for inviting me to give this guest lecture. So I'm very excited to share some of my recent work on clustering. So today I'll be talking about parallel algorithms for density-based as well as structural clustering. So I'll be talking about one clustering algorithm for spatial data sets and then another clustering algorithm for graph data sets. And this work is in collaboration with Yiqiu Wang, Yan Gu, Tom Zheng, and Lakshman Duopala, who are my students and postdocs. So the goal of clustering is to group together similar objects and to separate dissimilar objects from each other. And you can apply clustering to both spatial data sets as well as graphs. And for spatial data sets, we have an example on the upper right here. And here the similarity between points is defined to be their Euclidean distance. And we can see that we have two clusters here, the blue one and the green one. And within each cluster, every point has another point that's reasonably close to it. However, between different clusters, the points are further away. We also have these unclustered points called noise points, and these don't naturally belong into any clusters, and a clustering algorithm can also identify these as outlier or noise points. Now on the bottom right, we have an example of a graph where each color represents a cluster, and we see that we have a lot of edges within each cluster, but many fewer edges going across different clusters. And so this is sort of the kind of clustering that you would like for a graph data set. There's a lot of applications for clustering. For example, it can be used for community detection, finding groups of people with similar characteristics in social networks. It's also used for identifying groups of proteins or genes that have similar functionalities in bioinformatics. It can also be used for load balancing and parallel and distributed computing, as well as many other applications. And as such, clustering is a very well-studied topic, and there have been over hundreds of textbooks written on just the clustering problem itself. However, there's no universally accepted definition for cluster quality, and indeed many different metrics have been proposed for clustering, and therefore there have been at least thousands, if not more, different clustering algorithms that have been proposed due to all of these different metrics, as well as all of the application domains out there. So today I'm not going to be talking about all of these different clustering algorithms. I'm happy to refer you to some surveys and textbooks if you're interested, but I'm just going to talk about two specific clustering algorithms, one for spatial data sets and one for graphs, that have been pretty well studied in the literature and have shown to work very well for certain settings. So the first problem I'll be talking about is the DBSCAN problem for spatial clustering. DBSCAN stands for density-based spatial clustering of applications with noise. It was first introduced by Esther et al. In 1996, and it's a very popular algorithm that's widely used in practice. And in fact, this paper has already over 19,000 citations. So the goal of DBSCAN is to identify areas of high density to form clusters. So we want to find dense areas with a lot of points in that small area. And furthermore, DBSCAN doesn't require the number of clusters to be known beforehand. So that's one advantage of DBSCAN. Secondly, it's able to detect arbitrarily shaped clusters. And finally, it's robust to noise. So we have an example here on the right here. So we have a data set with two rings, and we see that DBSCAN is able to separate these two rings into their own separate cluster. But if you look at something like k-means, without applying any transformation on the data, k-means is actually going to split each of these rings into two different clusters if we're looking for two clusters. So this result is not as natural as what you would get for DBSCAN. Secondly, DBSCAN is able to classify some of these points as noise points. If you look at the example on the bottom, we have clusters, but we also have points that don't belong into any clusters because they don't seem to naturally fall into any of the three clusters here. But DBSCAN is able to identify this. If you run k-means, at least a traditional version of k-means, all the points would actually be classified into one of the clusters, and these outlier points can actually affect the quality of the clusters you get by shifting the center of the cluster. So that's DBSCAN. The other algorithm I'll be talking about is the SCAN algorithm for graph clustering. So SCAN stands for Structural Clustering Algorithm for Networks. It was introduced by Shun et al. In 2007. So SCAN is like DBSCAN, but applied to graphs instead of spatial data. And here the similarity of vertices is based on the number of common neighbors they have. And we say that an area is dense if there are many vertices who have many similar neighbors in the area. And just like DBSCAN, SCAN can identify both clusters as well as outliers. So in the example here, we have two clusters, the blue and the red one, and we can sort of see that inside each cluster, it's very well connected, but there are a few edges going across clusters. We also have this outlier point here that's uncolored. This is because it doesn't seem to naturally fall into any of the clusters, and it also doesn't seem very natural to put it in its own cluster. Okay, so our goal is to design high-performance parallel solutions to solve these two problems, DBSCAN and SCAN. As you all know, that we have a lot of very large data sets today, and that's why we want to use parallelism to speed up our algorithms. So in our work, we designed state-of-the-art parallel multi-core algorithms for DBSCAN and SCAN. We show that these algorithms not only perform well in practice, but they also have strong theoretical guarantees. And finally, they can process the largest data sets used in the literature for these problems using just a single multi-core machine much more quickly than existing solutions, which many of which are designed for distributed memory. So since I'm talking about theoretical guarantees, let me introduce the model of computation we're using to analyze the algorithm. So this is called the work-span model. So in the work-span model, we can model a computation using a directed acyclic graph, and each vertex in this DAG corresponds to a single unit of work that we want to perform. And then there's an edge between two vertices. If the task in the first vertex has to execute, it has to finish before the second vertex's task can begin. So it's a dependence. And we also see that some of these vertices enable multiple vertices to begin after it finishes. And this is where parallelism comes in. So if we have two vertices that are not connected by a directed path, then we can execute those in parallel. We don't necessarily have to execute those in parallel, but the runtime system is allowed to execute those in parallel. So in the work span model, we care about the work, which is the number of operations used by the algorithm. And in terms of this computation DAG here, the work is just the number of vertices in our DAG. And the work for a sequential algorithm is equivalent to the running time of the sequential algorithm. Secondly, we care about the span, which is the length of the longest sequential dependence in our DAG. So this is also the length of the longest directed path. And here we've shaded the vertices on this longest directed path in yellow. And this sort of tells us a limit to how much parallelism we can achieve. Because even if we have an infinite number of processors, we still have to execute these tasks colored in yellow sequentially. Now we define the parallelism of an algorithm to be the work divided by the span. So obviously, if you have a lower span algorithm, then the parallelism increases. But also, we don't want to have to increase the work in order to get more parallelism because due to a famous scheduling theorem by Brent, the running time of a parallel algorithm is upper bounded by the work divided by the number of processors plus the span. So we want to try to minimize both the work as well as the span of our algorithm. We say that a parallel algorithm is work efficient if its work asymptotically matches that of the best sequential algorithm for the problem. And the goal of our work is to come up with work efficient and low span parallel algorithms. We want low span because that increases our parallelism, and it's also one of the terms in the running time. But we also want work efficiency. We want the work to be as small as possible because usually if you have a low span algorithm, the first term here, work over P, is going to dominate your running time because the number of processors you're using for a multi-core algorithm is at most on the order of hundreds. And the work is going to be way more than that, at least for the problems that you care about parallelizing. So we want to come up with work efficient as well as low span algorithms. And we want to try to at least asymptotically match the work of the best sequential algorithm because that's sort of the best we can do, at least in theory. Okay, so now let me talk about the DBSCAN problem and our parallel algorithm for it. And after that, I'll talk about the SCAN problem for graph clustering. Okay, so let's first introduce the problem definition. So for DBSCAN, we have two parameters, epsilon and min points. And we classify a point as a core point if there are at least min points, many points in the epsilon circle centered around the point itself. So let's look at this blue point here. We draw the epsilon radius circle around it. And here we see that there are 3 points within this circle, including the blue point itself. So for example, if we set min points equal to 3, then this blue point would be classified as a core vertex because it has at least 3 points in this epsilon circle. We can do this for all the other points. So now I've shaded all the points that are core points with blue. The next step is we're going to connect these core points together if they're within epsilon distance away from each other. So now we have a graph where the points are vertices and then these edges are added if the points are within epsilon distance away from each other. And then with this graph, we find the connected components and each component gives us a cluster on the core point. So we have 2 clusters here, the blue one and the red one. Next, we have to deal with these unclustered points. So we say that a point is a border point if there are fewer than min points, many points in its epsilon circle. So this point here, if we draw the epsilon circle around it, we only see 2 points. So it's not a core point, but it does have a core point inside this epsilon circle. So then it can choose to join the cluster for this core point. And in general, if there are multiple core points from different clusters in the epsilon circle, it can choose to join any of those clusters. So these 2 blue points in squares are border points. They chose to join the blue cluster. And then this one up here, the square in red, chose to join the red cluster. And then finally, we have these noise points. These are points where when I draw the epsilon circle around them, they don't have any other core points in them. So they're marked with these crosses here. Okay, so that's the definition of DBSCAN. Now, there's been a lot of related work on DBSCAN, as you can imagine, since the original paper has over 19,000 citations. Here I'll just list the relevant work that's most related to our work. So in terms of sequential algorithms, these are the two papers that have the fastest algorithms for DBSCAN to date in theory. The first one by DeBerg et al. It presents exact algorithms for the 2D case. And then in Gan and Tao, they present a hardness result for d greater than 2. They also present some algorithms for d greater than 2, as well as an approximation algorithm that's much faster, at least in theory, than these exact algorithms. There's been a lot of parallel algorithms designed for DBSCAN. Here I'm just listing a subset of these. The one that's most relevant to our experimental comparison is this one from Sung et al. in Sigmod 2018. This was the most recent one at the time that we published our paper. But one thing about all of these existing parallel algorithms is that they're not work efficient. They take more work than the sequential algorithms. And the lack of strong theoretical guarantees makes them run slowly in practice. Even though they get high scalability, they have low work efficiency, as we'll see in the experimental evaluation later. So the contributions of our work include designing work-efficient parallel algorithms for DBSCAN. We also have highly optimized multi-core implementations, and finally, experiments showing that our algorithms outperform the state of the art. So here's a summary of the bounds that we prove in the paper for all of our algorithms in the different settings. So we have specially designed algorithms for the 2D setting, and then we have other algorithms for d greater than 2, 3D, as well as any other constant dimension. We also are able to parallelize the approximate algorithm by Gan and Tao, and here are the bounds that we get. So they're all work efficient. Compared to DeBerg et al. And Gan and Tao's paper, the approximation algorithm takes linear expected work, which is better than the exact algorithms that take at least n log n work. So for the rest of the talk, at least for DBSCAN, I'm just going to talk about the 2D algorithm. I'll briefly mention how you can extend the algorithm to higher dimensions, but I'm just going to do the analysis for 2D.
Julian, may I ask a question on the last slide?
Yeah, sure.
This approximation algorithms, what is the dependence on, usually you have then an approximation factor 1 plus epsilon or so. Do you remember what the dependence on epsilon is?
Yeah, I think it's just inversely proportional. So like I think it's like 1 over epsilon. But
large d, I would have feared that it's maybe 1 over epsilon to the d or so.
Oh, yeah, you're right. So I think there is an exponential dependence on d. So if you don't treat d as a constant, then it's right. There's basically a very, very big constant factor there. Yeah.
Okay. Thanks.
Yeah. Thanks for asking that. So in fact, like all of these bounds here for 3D and greater, they all have an exponential dependence on d. I just didn't write it on this slide, but just imagine that there is this 2 to the d factor. Okay, so let me first talk about the naive parallel algorithm in the 2D case, and then I'll talk about how we can improve upon it. So the naive parallel algorithm, what it does is for every core point, it's going to issue a range query of range epsilon to see how many points are within this radius. And then if there are at least min points, many points inside this radius, it will mark the point as a core point. And then, of course, we need to do this parallel connected components on the core points to get our clusters. But the range queries are the part that takes a lot of work. So in the worst case, they take linear work per point. Because the range could actually consist of a constant fraction of your points in the data set. So therefore, in the worst case, this naive algorithm will take quadratic work. And many of the existing parallel algorithms for DBSCAN use this approach or some variant of this approach, and they take quadratic work or even more. So now let's see how we can improve upon this for the 2D case. So our algorithm is first going to construct a grid on our points. So the cells of this grid are going to have side length epsilon over square root of 2. And this guarantees that any points that fall within the same cell will be within epsilon distance away from each other, since the diagonal of the cell is of distance epsilon. So what we're going to do is we're first going to sort all the points based on the cell ID that they belong in. And you can determine what the cell you belong in just by doing some arithmetic on your X and Y coordinates. And then now, once we have all the points for each cell contiguously in memory, that allows us to easily just insert these non-empty cells as well as the points in them into a parallel hash table so that we can access them efficiently. Next, we're going to determine which points are core points. So how do we do this? So let's consider this blue point here. We're first going to determine what cell it belongs into. So it belongs in this blue cell here. Now we want to find how many neighbors this blue point has within its epsilon circle. So it turns out that we only have to check 21 cells to get all of the neighbors that are within epsilon distance away. So we check this blue cell as well as the 20 neighboring cells around it, and we can show that for any point within epsilon away from this blue point, it has to lie in one of these 21 cells. So then we can just check all of them and loop over the points in each cell and then count how many are within epsilon distance away. There is one important optimization which is needed for both theory and also practice, which is for the cells that have at least min points many points in them, we're actually just going to mark all the points as core points because we know that there are at least min points many points, and all of these points are within epsilon distance away from each other. So we know that they're all core points. So we don't want to waste too much work for these. After we identify the core points, we're going to construct what we call the cell graph. So the cell graph is going to have these cells as vertices. And here I've labeled a cell as a core cell if it has at least one core point in it. And then we have these non-core cells which have a non-core point in them. So what we're going to do is we're going to construct a graph. So we're going to try to connect these core cells together. And how do we do that? Well, for each cell, we're going to issue a BCP connectivity query with each of its neighboring cells that are non-empty. And what the BCP connectivity query does is it takes two cells and it returns true if there is a pair of points, one from each cell that's within epsilon distance away from each other. So these are the edges that get added. We have these blue edges here and these red edges here. These are added because the BCP query returned true. And then now we'll construct this graph and run connected components on it to get the components of these core cells. So now we have this component of the blue core cells and the component of the red core cells. So now all the core points within these core cells know what cluster they belong in. They're just going to take the cluster corresponding to their cell. Finally, we have to cluster the border points. And for these border points, we'll just do this approach of checking the 20 neighboring cells, and we'll see if there's a core point within one of these 20 neighboring cells that's also within epsilon distance away from the border point, and if so, then we'll choose to join one of those clusters. So again, these blue squares join the blue cluster, the red square join the red cluster, and then we have these noise points because they don't find any any core points within their epsilon circle. Let's briefly go over the analysis. All the bounds hold with high probability because the parallel primitives we're using are randomized. So the first part is to construct these grid cells. So we want to sort the points according to which cell they belong in and then insert them into hash tables. So we use a semi-sorting algorithm to do that, which basically just groups together points that belong to the same cell together, but it doesn't guarantee any ordering across points belonging to different cells, but this is sufficient for our purposes. And then we build a parallel hash table. We insert all of these non-empty cells as well as their points into the hash table. So this part takes linear work and logarithmic span. Now for the second part, this is to mark the core points. So recall that each core point is going to check the 21 cells in its neighborhood to see how many points are within its epsilon radius. But the optimization that we said earlier is that each cell with at least min points, many points is going to just mark all the points as core points. So with some analysis, you can argue that every cell will only be checked by 21 times order min points many other points, because the other cells that check with this cell have at most or have less than min points many points in them. Otherwise, they would have just used the optimization. And there are 21 other cells in the worst case. So we have 21 times order min points many points to check each cell. And then each point also has to do a parallel reduction to figure out how many points are within their epsilon radius. So that takes logarithmic span. And therefore, in total, the range queries are going to take order n times min points work in logarithmic span. Now we built this cell graph on the core cells. And one way to do this is to construct a Delaunay triangulation on the core points, and then just keep the triangulation edges that are of distance at most epsilon away from each other. This will give you the correct cell graph. I'm not going to prove it here, but the paper by Gan and Tao actually has a proof of this. So you can read that if you're interested. We also describe other approaches to do this in the paper, but the Delaunay one is the most, the easiest one to think about. So using a parallel Delaunay triangulation algorithm, we get a order n log n work and order log n span routine for building this cell graph. Then we run connectivity on this cell graph to find the clusters, which takes only linear work and logarithmic span. And then finally, we have to cluster the remaining points, the border points, and the process for doing this is similar to marking the core points. So the analysis is also similar, taking order n times min points work and logarithmic span. So in total, our algorithm is going to take order n log n work and logarithmic span, assuming that min points is a constant. If it's not a constant, then you would add it here. So you would get n times log n plus min points. Okay, now to extend this to higher dimensions, we're going to change the side length of our cell from epsilon over root 2 to epsilon over root d. And this guarantees that points falling within the same cell are within epsilon away from each other. And then we also have to change how we compute the BCP queries. So for 2D, we can use Delaunay triangulation, but for higher dimensions, that becomes more expensive, taking at least quadratic work. So there are other ways to do this, which we describe in the paper. Overall, we get work efficient bounds. So n log n for 2D matches the sequential bounds. And then for d greater than 2, our algorithm takes sub-quadratic work, which is better than the naive parallel algorithm, also matching the best sequential bounds. And then finally, for approximation, it's linear work, ignoring the constants here that depend on the dimensionality. This is easier to do for the approximate case because we can tolerate some error in the answers that we return. But for all of these algorithms, the BCP queries dominate the work. And then for all of these other algorithms, we also implement all the operations in parallel and polylog span. So I already talked about hashing and semi-sorting, Delaunay. We also use these other primitives throughout our algorithms. Okay, so that was the theoretical algorithm. Let me talk about some optimizations we did for our implementation. So first of all, we said that we have to loop through all the neighboring cells and see how many core points we have within those cells. This is fine for 2D, but as you increase the dimensionality of the data set, the number of cells you have to loop over grows exponentially. So we found that it was actually cheaper to maintain the non-empty cells in the KD tree. And then now whenever a point wants to find its neighboring cells, we can just query this KD tree and return the non-empty cells around this around the epsilon radius. So this saves a lot of work for the higher dimensional data sets. Another optimization that we did was to prune some of the BCP queries that we executed. So for the case without pruning, let's look at cells 1 and 2. So 1 is going to execute 4 BCP queries, and these are indicated with the blue edges here. And then the second cell is going to execute 6 BCP queries. So in total, we're going to execute 10 BCP queries. But now let's see what we can do is if we can do pruning. So Simon asked if the KD tree is already better for d equals 3. I think for d equals 3 it was about the same, but for d equals 5 and larger, the KD tree definitely had a big advantage. For d equals 3, I think it was sometimes faster and sometimes slower depending on the data set. Great. So now let's see how we can do pruning. So first, we use a parallel union find data structure to keep the connectivity information on the fly. This idea was used in the sequential algorithm by Gan and Tao. And now we can prune some of these queries as follows. So we can first prune queries if the two cells they're querying are already connected. And this can be determined by doing a find on the two cells in our union find data structure. And then secondly, we'll prune queries if it's a repeated query. So if cell 1 already queried cell 2, then it's not going to do the opposite query from cell 2 to cell 1. So let's see what happens if we execute these, if we process the cells sequentially. So cell 1 is first going to execute these 4 connectivity queries. Let's just say they all return true, for example. Then what cell 2 is going to do is when we execute the queries, some of these are going to be pruned. So first of all, the query from cell 2 to cell 1, that's a repeated query, so we don't have to do that. Then for the queries for cell 2 to these 3 other cells, which are indicated with this dotted edge, well, those can get pruned out because cell 1 already connected to those 3 cells. Cell 1 also connected to cell 2 already. So by transitivity, cell 2 is connected to these 3 cells. And we don't have to execute the BCP queries for those. And then finally, there are these 2 remaining queries that have to be executed because we haven't actually looked at these 2 cells yet in our example. So with pruning, we get the number of queries down from 10 down to 6 for this example. And this is important because most of the work in our implementations are done in these BCP queries. We want to do as few queries as possible. We also found that the order in which we process the cells affects the pruning quality. So if we're able to process cells that connect to many other cells early on, then that allows us to prune many more queries later. So sequentially, we can actually use a heuristic to try to order the cells, order the cells, and then process these cells in our determined order. And the heuristic we use is basically the number of points in the cell, because a cell with more points in it will tend to connect to more other cells. But in parallel, it's a little bit harder to control because we have multiple threads executing these queries for different cells in parallel. So to make the pruning quality better in the parallel setting, we bucketed the cells based on the number of points they had in them in powers of 2. And then we processed each bucket in decreasing order of this number of points. And each bucket can be processed completely in parallel, but we synchronize between different buckets. So this makes sure that the cells that connect to more other cells will be processed early on, leading to more queries being pruned later. Okay, so now on to some experimental evaluations. So we ran our experiments on 2 AWS machines. One is a 36-core machine, the other is a 48-core machine. We only used a large machine for the larger data sets that didn't fit on the 36-core machine because the 36-core machine was a more powerful machine. So here we're plotting the speed up of our best exact algorithm over the best sequential algorithm. Turned out that the fastest sequential algorithm in our experiments was actually our own parallel algorithm run on a single thread. We tested the existing implementations. The fastest ones were by Gan and Tao, but we found that we were about 5 times faster than their implementations due to some additional optimizations we had. Here we're also comparing against 2 multi-core implementations. These implementations were designed specifically for multi-core machines, but unfortunately they don't actually scale very well compared to the fastest sequential algorithm, whereas our algorithm is able to get about a 32x speed up on 36 cores with hyperthreading. This is done on a 3D data set with 10 million points, but we found similar trends for other data sets as well. Here we're plotting the self-relative speedup instead of the speedup over the same sequential baseline. So the green line is still the same because our baseline is the same here, but we see that the 2 other implementations do actually get some self-relative scalability here. It's just that because they're inefficient, though, they take much more time than the sequential algorithm, even on 36 cores. So we see a flat line here. And across all of our experiments, we found that we were between 16 and 6,000 times faster than these 2 existing multi-core implementations. We also compared to this more recent distributed memory implementation called DBSCAN. This implementation was able to scale to much larger data sets. So these are the data sets that we compared with. So the largest data set is this teraclick log data set with over 4 billion data points in 13 dimensions. This is also the largest data set used in the literature for exact DBSCAN algorithms. And for DBSCAN, we were able to download their code and run it on our 48-core multi-core machine. But they also reported numbers in their paper for 48-core distributed clusters. So we basically took the best times from the two settings and reported that for DBSCAN. But we were still able to beat it significantly between 18 and 577 times for these different data sets across varying parameters.
Maybe I can ask another question here.
Yeah, sure, Peter.
So my experience is that, so what I understood you like this, that this distributed codes on a single compute node, they are much slower than yours.
Right, right.
Would also be interesting to see whether they actually, whether it actually helps to use more or less arbitrary amount of distributed memory parallelism. I would guess that even using hundreds or thousands of compute nodes, they wouldn't get faster than your single node code. Or
yeah, so I think for DBSCAN, I mean, I think that like the communication cost is the dominant overhead here. So I think even if you increase it to like thousands of processors, I mean, it might get faster, but I don't think it will be as fast as the single machine solution. I think for things like we were able to download their code and run it on our machine, but their code doesn't actually take advantage of shared memory. So I think that code can probably be optimized if you knew that you were running in a shared memory setting to basically take advantage of the shared memory. And I think that could actually improve the performance by, I mean, I don't know by how much, but by some constant factor. Yeah. So,
yeah, thanks.
Yeah, thanks. Yeah, so here we're testing the performance as a function of min points as well as epsilon. So we say that our performance gets worse as you increase min points. This is because in our work analysis, you saw that there was this part for marking core points and border points that takes time proportional to min points. Whereas for the existing two multi-core implementations, their running time is dominated by these range queries, which don't depend on min points. So we see two flat lines for them. Now, if we increase epsilon, we get our performance actually gets better because in our grid structure, we have fewer cells. And now that means when constructing the cell graph, we have fewer BCP queries to issue. So that's why our performance gets better. Whereas for the existing implementations, their performance gets worse because the range queries which dominate the running time get slower as you increase epsilon because you're searching a larger radius. Great. So that was the part for DBSCAN. Now let me talk about our work for SCAN for graph clustering. And let me first go over some definitions first. Actually, before I do that, does anyone have any questions on the DBSCAN part? I'm happy to take any other questions. Okay, if not, then I'll wait till the end to answer the questions. In SCAN, we define a pair of adjacent vertices to be similar if they share many common neighbors. So in the original SCAN algorithm, they use a similarity metric called cosine similarity. So how does this work? Well, for now, let's say we're going to define this neighborhood function n to return all the neighbors of a vertex as well as the vertex itself. So it contains an additional vertex compared to the traditional notion of neighborhoods that you might imagine. And this is just to make the notation easier because I don't want to have to add one everywhere to include the vertex itself. So what we do for vertices u and v is we compute the intersection of their neighborhoods and take the size of that divided by the square root of the product of the two neighborhood sizes. So let's say, for example, we want to compute the similarity between f and g in this graph. Well, we first figure out the neighborhood size of f. It's 4 here because we're including e, g, h, as well as f itself. Now, same for G, it has a neighborhood size of 4. And then also we compute the intersection. The intersection contains 3 vertices, F, G, and H, and the size of that is 3. So that we can just now plug this into our formula up here, and that gives us 3/4.75. And in general, a SCAN algorithm is going to compute the similarity scores for all the edges in the graph. There are other similarity metrics you can use. We consider Jacquard similarity as well as weighted cosine similarity for weighted graphs in our paper. Some other SCAN papers also consider these metrics, but for the rest of this talk, I'm just going to talk about the cosine similarity metric. The ideas are similar for the other metrics. Now, the SCAN problem takes as input 2 user-selected parameters, mu and epsilon. And just like in DBSCAN, we say a vertex is a core vertex if it has at least mu neighbors that are epsilon similar to it. Their similarity score is at least epsilon. So now in this example here, let's say epsilon is 0.6. Now we can actually label each edge as either having similarity less than epsilon or similarity at least epsilon based on the similarity of the 2 endpoints. So I've shaded the edges that are at least epsilon similar in green and the other edges in red here. Now we can figure out which of the vertices are core vertices. So let's say mu is 3. That means each vertex needs at least 3 neighbors that are epsilon similar to it. So here I've shaded the vertices that are core vertices in blue. So we can just check one of them to make sure it is a core vertex. So let's check A. So A, well, first of all, A is its own neighbor based on the definition of neighborhood we used. And it's itself, it has a similarity of 1 just by definition. And then it also has 2 neighbors that are epsilon similar to it, B and D. So therefore, it has 3 epsilon similar neighbors in its neighborhood, and it gets classified as a core vertex. The next part is to find the connected components of the core vertices along with any other epsilon similar neighbors they have. So here we get 2 connected components. The first one is A, B, C, D. Second one is F, G, H, but we also have this non-core vertex J here, which we call a border vertex because J is epsilon similar to a core vertex. It's just not a core vertex itself, but it can join the cluster for the core vertex. This is analogous to the notion of border points in DBSCAN. And then finally, just like in DBSCAN, we have these outlier points, E, K, and I, because they don't have any epsilon similar neighbors that are core vertices. So the work of the SCAN algorithm, sequentially, it's going to be order m times alpha. Alpha is called the arboricity of the graph, which is a measure of the sparsity of the graph. And it gets bigger as you increase the density of the graph. But alpha is upper bounded by square root of m. So therefore, order m alpha is at most order m to the 3 halves. In the SCAN algorithm, the most expensive part is computing the similarity scores, and that takes order m alpha work. And this is due to a triangle counting-like procedure to count the number of common neighbors. And then after you get the core vertices as well as their epsilon similar neighbors, you can run a connected components algorithm in linear time to get your clusters. But because of this dependence on arboricity, SCAN becomes especially costly for dense graphs, as we'll see later. Another issue with SCAN, this is also an issue with DBSCAN, is that oftentimes users have to try many different parameters in order to obtain good clusters. And every time you try a different set of parameters, you have to rerun your algorithm. And this could take a lot of time. For SCAN, this is very expensive, especially for dense graphs. So recently, there was a data structure proposed called GS Index by Wen et al. In 2017, which pre-computes a bunch of information such that whenever you want to query for clusters under some value of mu and epsilon, it becomes much quicker than running the SCAN algorithm from scratch. So the 2 main components of their data structure are as follows. So we have a neighbor ordering, which allows you to quickly find all the epsilon similar neighbors of a vertex. And to do this, well, each vertex is going to sort its neighbors in decreasing order by the similarity. And now if you want to find all the neighbors that are at least epsilon similar to yourself, you just take a prefix of this sorted order. The other data structure is called the core ordering structure, which allows you to quickly find the core vertices given a particular value of mu and epsilon. So for each mu, we're going to store a list of vertices sorted in decreasing order by the maximum value of epsilon that they can take, such that the vertex is a core vertex. So let's look at an example here to get more intuition. So here's our example graph again. Here's what the neighbor ordering would look like. So each vertex has a list of its neighbors. For D, I've labeled the similarity scores of its neighbors here. And these similarity scores are going to be sorted in decreasing order. So D is the most similar to itself. That has a similarity score of 1, followed by B, which has 0.89 similarity score, and then A, C, and E. Now, if we pick any value of epsilon, say 0.6 in our example, we can basically scan our neighbor list until we get to a vertex that's below our threshold. We get to E here, which is 0.52, less than 0.6, and then we just cut it off. So our epsilon similar neighbors are going to be a prefix of our sorted list. Now for the core ordering, for every value of mu, we're going to create a row in this data structure. And we're going to sort these vertices in decreasing order by the maximum epsilon at which it can be a core vertex. So how do I get these maximum epsilon values that I've labeled on these vertices? So again, let's take D, for example. There's a value of 0.77. So how do I get that? Well, for the particular value of mu I'm looking at, I'm going to go to the muth neighbor in D's sorted neighbor list. And this gets me to vertex A, which has a similarity score of 0.77. So that's where the value comes from. And why does this make sense? Well, if I picked an epsilon value that's smaller than 0.77, say 0.6, well, then D is going to have at least mu many epsilon similar neighbors. But if I picked an epsilon value that's greater than 0.77, say I picked 0.8, well, the epsilon similar neighbors for D is going to get cut off here. It's only going to have D and B, and therefore it doesn't have enough neighbors that are epsilon similar for it to be a core vertex because mu is 3 here. Okay, so now with this sorted order here, again, we can just do a sequential scan. If we get fix the value of mu and epsilon until we get to a vertex that's below our threshold, and then we cut it off. So again, it's a prefix here where we want to get all the core vertices. And then after we get the core vertices and their epsilon similar neighbors, we'll run a BFS-like procedure to find our clusters. Okay, so the work for computing this index is order alpha plus log n times m. The alpha m is the same as before. We have to compute these similarity scores, which use a triangle counting like procedure. But the m log n term comes from having to sort these neighbor lists and the core ordering list. Now the work for querying for clusters is much better than before. The work is just going to be linear in the total sizes of the cluster. And in fact, you don't even need to do work for the non-epsilon similar edges and the unclustered vertices. We only have to look at the core vertices and their epsilon similar neighbors. So this could even take work that's sublinear in the size of your graph if the clusters you get back are small. So the nice thing about GS index is that queries are fast, but computing the index is still slow because the original data structure was sequential. So in our work, we came up with a provably work efficient parallel algorithm for constructing this index that also has logarithmic span. And even with our parallel algorithm, we found that the similarity computation was the bottleneck. So we introduced approximate similarity computation via locality sensitive hashing to further improve the performance. And then finally, we have implementations and we compare with state of the art, showing that we can get significant speed ups in practice. So now let's talk about the parallel algorithm. So I said earlier that finding common neighbors is similar to triangle counting, and let's see why this is the case. Well, if I want to find the common neighbors for F and G, well, I'm only going to do this for pairs of vertices that are connected based on the definition of scan. And now if they have a common neighbor H, well, it has to have an edge from F to H and an edge from G to H, and this forms a triangle. So basically what we can do to find the shared neighbors is to run triangle counting and count the number of common neighbors that each pair of vertices that are adjacent have. And this can be done in order alpha m work and logarithmic span with high probability using parallel hash tables as part of the triangle counting subroutine. But even this is kind of slow. So we want to further optimize the similarity computation since it's the bottleneck. So one optimization we use, it's a well-known optimization for triangle counting, is we're going to direct the edges in our graph from lower degree to higher degree endpoint. And then we're only going to look for triangles that satisfy a particular orientation of our directed edges. And this allows us to count each triangle just once instead of 3 times as we would need to do in our undirected graph. And then secondly, for better cache locality, instead of using parallel hash tables, we opted to use a more cache-friendly parallel merging subroutine to find the intersection between sorted neighbor lists. Now for computing the neighbor and the core orderings, well, the sequential algorithm uses a comparison sort on these similarity scores. So we can easily just plug in a parallel comparison sort here. But we observed that we can actually use integer sort as long as the graphs are unweighted in order to get better work bounds. So even though the similarity scores that we're sorting are not integers, we can transform them into integers in a polynomially bounded range using this formula here. And this transformation preserves the relative order between 2 similarity scores. So by using integer sort, we're able to reduce the log n term in this work bound down to either constant or log n, depending on which integer sorting algorithm we use. So if we use a work efficient parallel integer sort, well, the work is alpha m, but the span is actually not polylogarithmic. It's order n to the beta for some small constant beta. And if we really want to get logarithmic span, we can use a slightly less work efficient parallel integer sort, which takes m log n work. But both of these work terms are already better than the original work bound. Okay, now after we compute the sorted order of these neighbor and the core ordering lists, well, now when we want to do a query, we have to basically find this prefix of vertices to return. So sequentially, we were scanning this one at a time, which is not very parallel. So instead, we use a doubling search. We first check 1 and then 2 and 4 vertices until we get to a vertex that's below our epsilon threshold, and then we'll then do a binary search within that last interval to figure out where to stop. So this is work efficient. It takes at most twice the work as the sequential process. Now for running parallel connectivity, again, we can plug in this linear work logarithmic span connecting components algorithm. But just as in DBSCAN, we found that it was faster to use a parallel union find data structure to maintain these clusters on the fly. Because in this case, we don't have to generate this subgraph, which is induced by the core vertices and their epsilon similar neighbors, and then pass it to some other connected components routine. So that saves us a pass over the data. Okay, so that's our parallel algorithm, at least for exact similarity computations. But we found that still the similarity computation was the bottleneck. So we decided to explore using approximation to speed this up. And this gave us significant benefits, especially on dense graphs. So we use locality sensitive hashing, or LSH, in order to approximate the similarity between 2 vertices. LSH is a scheme designed to measure the similarity between 2 sets approximately. And in our case, the 2 sets that we're measuring the similarity between are the 2 neighborhoods of the vertices that we're trying to compute the similarity for. So there are some well-known schemes for LSH for these similarity metrics that we use. So SimHash works for cosine similarity, MinHash works for Jacquard similarity. There is this parameter, which is the sample size for these LSH schemes, which trades off between accuracy and running time. So if you increase K, your estimate is more accurate, but the running time also increases and vice versa. So for a particular sample size K, we can basically get these work bounds here. So we can reduce the order alpha plus log n times m work bound down to either order km or order k plus log n times m, depending on the parallel integer sorting algorithm we use. So we got rid of this log n with parallel integer sort, and then we changed the alpha to k using LSH. And then for dense graphs where alpha is large, then it's pretty easy to find a value of k that's smaller than alpha while giving good approximation guarantees as well as running time. In the paper, we also proved that if the number of samples k is sufficiently large, something like logarithmic times some constants depending on epsilon, we can correctly classify all the edges as either above or below epsilon in similarity, except for this small interval around epsilon where we're not able to guarantee that these edges are classified correctly with high probability. Okay, so we implemented this LSH approximation scheme, but we found that just like as the theory predicts, it was actually faster to do the exact similarity computation when we had at least one low degree vertex that we were comparing, and it was better to use LSH when both of the vertices we were comparing had high degree. So our solution was to use a hybrid approach where we only use LSH when comparing pairs of high degree vertices and use triangle counting everywhere else. All right, so now on to some experiments. So we ran experiments on a 48 core machine with two-way hyperthreading for a maximum of 96 hyperthreads. We first compared to the fastest parallel scan algorithm called PPSCAN. This is not an index-based algorithm because there aren't any existing parallel index-based algorithms. This is just a regular scan algorithm that will run the similarity computations from scratch every time. We also compared to the original sequential index-based scan algorithm, GSIndex. And here I'll show the results for two data sets. We have more in the paper if you're interested. First is the Friendster graph with 1.8 billion edges. This is a relatively sparse social network graph. The other one is this cochlea graph, which is a dense weighted biological graph with only 26K vertices, but 282 million edges. On the right, we have the index construction time for our algorithm in parallel, our algorithm on one thread, and GSIndex on one thread. We don't have data for GSIndex for cochlea because their implementation doesn't work for weighted graphs. But for Friendster, we have data. So we see that even our single-threaded construction time is better than GSIndex's. And this is due to the triangle counting optimizations that we implemented. So across all of the experiments, we found that we got a speed of between 1.4 and 2.2 over GSIndex on a single thread. And then now when running on 96 threads, we got a speed up of between 23 and 70x over our single threaded running time. The speed ups were lower for the smaller data sets just due to less work to parallelize over, and it was larger for the bigger data sets. Now we compare the query time of our algorithm GSIndex as well as PPSCAN, which is a non-index based algorithm. Here we're fixing mu to be 5 and varying epsilon. We also did it the other way around in the paper, but the trends were similar. So the query time is on the y-axis, epsilon is on the x-axis. Our algorithm is this, our parallel algorithm is this red line. Our sequential algorithm is the blue line. GSIndex is the green line. PPSCAN is the purple line. Again, we don't have data for PPSCAN for cochlea because PPSCAN doesn't work for weighted graphs. And we see that we're faster than PPSCAN for all of these different values of epsilon. And across all the experiments, we found that we were between 1.2 and 12,000 times faster than PPSCAN. This is sort of not surprising because we pre-computed this index so that queries are fast, whereas PPSCAN has to do the similarity computation every time. But we also looked at the index construction time and added it to the query times. And we found that with just as few as about 10 queries, even if we include the index construction time, our algorithm was still faster than PPSCAN. And then secondly, well, we compared to GSIndex. First, we see that on one thread, we're slightly slower than GSIndex. This is just due to some additional computation we have to do to make our algorithm parallel. But on 96 threads, we got between a 5 and 32x speed up over GSIndex. And our self-relative speedups are even bigger. So it's about between a factor of 1 and 2 larger if we were comparing to our single thread running time. Finally, let's look at the approximate similarity computation. So here I'm plotting the modularity of the clusters, which is one of the metrics for cluster quality versus the index construction time. For both Jacquard and cosine similarity. For the exact schemes, we have one data point for each. For approximate, we have multiple data points because we can vary the sample size to get a different trade-off. And for the Friendster graph, we see that with less time, we can get clusters that are almost as good or even better than the exact algorithm. And then for cochlea, this is even more apparent. We see that with about 1/5 of the index construction time, we get clusters that are just as good as the exact algorithm. This is because this cochlea graph is a dense graph, which is where the LSH schemes perform very well in. Okay, so let me now conclude. So I talked about theoretically efficient and practical parallel algorithms for DBSCAN as well as SCAN for clustering spatial points as well as graphs. The code for this work is publicly available. So if you're interested in using this in your research, please feel free to check out these links here. And finally, I'm happy to take any additional questions that anyone might have.